Okay, good. Welcome back, everybody. Today's Thursday. Today we have a quiz, right? Quiz of what? What quiz?
3A. That's
No, that's Monday.
That's 2B.
2B. So today's quiz is going to cover 2B, and then you turned in homework of 3A already this morning, and then on Monday you're going to take the quiz of 3A. Okay. So I hope you keep working on it. It's quite important, okay? Let's just continue doing that. Summer is short, okay? So let's just begin today. All right, continue on what? This. So we're going to pick up what's left off on page 9. Trust analysis, class example 362. Let's just take a look. Okay. So in last class, we basically took care of the zero force member. Right here, member DB is zero force member, right? So we just completely ignore this member. You're going to just remove it from the original structure. This is a sign supporting structure. A sign is subjected to a wind loading. Looks like 300 pounds applied at the joint C and also joint B. 300 pounds force, horizontal force. This is due to the aerodynamic drag, I believe. And determine the force in each member of the truss and state if the members are in tension or compression. Okay, so before we even begin, we want to find out certain things. Okay, what is the strategy? You can solve this program in a variety of ways. You can, of course, choose most efficient way or least efficient way. What is the least efficient way? Well, let's just start talking about if you were to solve this program as a part of the final exam, where do you begin? Of course, I welcome your long answers. Long answers are actually very important. Go ahead.
Remove the zero force members.
Yeah, remove zero force member to begin with. That's good, actually. Very positive. What's next after that?
Free body diagram.
Free body diagram is, of course, yeah, important. But after you, let's say, okay, let's just draw a free body diagram then. I'm going to draw a free body diagram. Is the free body diagram for entire thing?
No.
No? Free body diagram for what?
Because you take out the thing that zero force.
That's right. So I remove this zero force member, and then do you want to draw a free body diagram?
Yeah. But you don't mean
For what? Free body diagram for, again, I keep asking, free body diagram of entire thing?
Then replace A and B with the forces.
So you're saying, okay, I'm going to draw a free body diagram of this entire thing and then try to find out what did you say? Support reaction at the A and B.
Yeah.
Hmm. You want to say something?
Yes, so you can
Yes, Sean?
also use the members. As
Members.
well. So instead of the joints. That makes sense.
Okay. Looks like I didn't do any of those. Holy cow, why? I didn't draw a free body diagram of entire truss structure. I actually started all of a sudden with joint C. You know why? I don't need to know those support reactions sort of thinking. That's what I'm thinking. That's what I'm thinking. Oh, do I need to know support reactions? This problem I actually didn't need to know. Okay, let's just begin with joint C. So this is my strategy, okay? Starting from joint C, free body diagram of this joint gives you 300 pounds force acting joint C horizontally, okay? Please, no electronic device in classroom. Sorry, please store it away. I'm sorry about that. Or you can step out of the classroom and look at outside. Either way. Okay, which one do you choose? Thank you. Okay, so this is member CB, member CD. internal force is developed for those two members, right? If you apply summation of force in x and y direction, you can find out those two unknown internal forces for those two members. That's it. Okay, so drawing joint C as a free body diagram, you can find out internal force for those two. That's first step I would do. Okay. After that, knowing this internal force, I'm going to pick up the joint B. Joint B, ignoring this, you have two unknowns. This is known already, so you can find out this and that. Okay? And after that, what? I'm going to pick up this. Pick up this means that this internal force is equal to this internal force anyways. That's it. Everything's done. I don't need to know reactions. Does it make sense? So this is the strategy I'm going to choose. Do you follow? So of course, first step. Okay. Zero force member. This is completely ignored. This is 0. So you can basically say F BD is equal to 0. So one answer already given by just observation. Why this is zero force member? Could you please tell me that? Why this is zero force member? Because this is collinear. Well, member CD, member D, those are collinear. If so, third member is zero force member because internal force here, internal force here must be equal and opposite. Okay? Equal and opposite. Yeah, that's right. Equal and opposite. If it's compressive here, this is tensile, vice versa. Okay. Well, no, isn't. It's the same. Sorry, not the equal and opposite. It's the same. If this is tensile, this is also tensile. If this is compressive, this is also compressive. That's what it is. Sorry about that. So I'm going to begin with joint C. Okay, so I'm going to pick up a joint C right here. Okay. So here is C. Now obviously external force 300 pounds is acting horizontally to the positive x direction, 300 pounds. And obviously internal loading member BC. So this is FBC unknown. And the other one is FCD. Okay. Okay. So first of all, I'm kind of wondering, the geometry-wise, what is this angle? Can you tell that?
45.
It's not 45. Actually, 45 is here. I'm talking about joint C. So the angle-wise, what I want is this angle. This is not 45. But one thing I know is this is a right triangle, isn't it? Okay. So let's just pick up a right triangle. Okay. So this is a CDB, right triangle. Okay. And then you know this is a 12 feet. This is a 13 feet. This is a 5 feet. And then what I want to know is this angle here. What is that? What is this angle here?
30.
Eh? This is 90 degrees. 13, 12, 5 feet. What kind of thing do you need? This is 90 degrees, so you're going to take probably inverse of sine or cosine or tangent, whatever. But this angle is here, so I would probably take either cosine or sine. Let's just take inverse sine. Inverse sine of 5/13, isn't it? Or inverse cosine of 12/13. Either way, it's fine. But you can get angle. What's the angle? 22.62 degrees. Great. This is the angle. Okay. So this is important information to begin with. So let's just apply for this joint C. Two unknowns, FCD and FBC you want. summation of the force. Let's set this is a positive x direction. Summation of the force in x direction set equal to 0. This is the 300 positive x direction minus FCD sine of 22.62 degrees set equal to 0. This is going to give you FCD. FCD is 780 pounds. Okay? Now, obviously, you don't want to start with the summation of force in y direction, because if you do that, you have one equation, two unknowns. It's not good. So again, when you apply summation of forces in certain directions, you carefully choose so that you can determine at least one unknown. In other words, this is one equation with one unknown, which is very simple to find out FCD to begin with. Okay? So if you flip-flop the process, you have to deal with all of a sudden two equations with two unknowns, simultaneous solution. It's going to take more time to do that. Okay?
Did we need to find the angle?
Angle is 22.62.
Couldn't we have just used the ratio of the sides?
You can do that, of course, if you want to. Because sine is essentially ratio. Cosine, tangent is essentially ratio. So it's the same thing. But anyway, summation of the force in y direction, let's just set equal to 0. This is going to be 780 cosine 22.62 degrees minus FBC set equal to 0. Again, so this is going to be FBC is equal to 720 pounds. Okay, so this is a joint C. All right. So since I assume the direction of the force, I assume to be FBC is a tensile, FCD is compressive, and then we get both positive values. So that means this is FCD, this is FCD is what? FCD is compressive, isn't it? Okay?
That's what I was.
That's what you say. Okay. The FBC is what? Tensile. Okay, good. All right. Next is, well, we're going to move on to joint B or D, but, well, there's no joint D because we removed it. Joint D basically says, you know, this member and that member has the same exact force. So since you know FCD, well, FCD is 780, so you can basically tell FDE is same, isn't it? Joint D. This is easy one, so let's just take a look at joint D. So joint D is, okay, well, you know FCD, which is,
Professor,
go ahead.
can you show again how we decided compressive and tensile force?
Okay, so this is once again the same discussion of yesterday's. Okay, so okay, so joint C. Okay, joint C's got, now you know, two members. Okay, let me just draw it a little bit bigger. Suppose you just introduce a virtual cut here, and then you know this is FBC. This is FCD. You know that.
Right.
You found it. Now, if you introduce the other member, equal and opposite shows up.
Right. Okay. Okay.
Yeah, we internal force. Okay, so this is compressive. Equal and opposite. So in other words, you can only look at it by introducing. Okay, let's just introduce virtual cut. Okay, let's just cut here, and then cut here, and pick up this member and that member, And this member is compressive, as you can see. Compressive. And again, this is again virtual cut, okay? So this member is a tensile, isn't it? This is a tensile. Okay. So that's what this thing is. Yep. This is actually interesting practice. You know, if you get confused, you can always do this technique. Okay. Introduce virtual cut and find out, internally speaking, is this tensile or compressive? That's what you're trying to find. Yeah, anyways. Okay. So the next step is joint D, obviously this, that's it. This is two members creating joint D, and then we do know this is FDC, which is equal to FCD, which is equal to, we found 780 pounds tensile, not compressive, sorry. So if you do summation of the force in this direction, not necessarily x or y, summation of this direction, summation of this direction force must be equal to 0. This really means that, okay, FDE is equal to FDC, which is equal to 780 pounds, again, compressive. So this basically tells you, hey, the internal force of this member and that member is the same thing. Both compressive force, 780 pounds, very easy. Okay? So now, so far, we found this and this and that. This and this and that. So we want those two. So obviously, joint B is the next choice. Okay? So we're going to choose the joint B. Let's just zoom in. Zoom out here. So far, this member we know, this member I know, this member I know. So let's just choose this one to find out the rest of two members. Joint B. Okay. So joint B, I'm going to draw once again free body diagram at the joint B. This is a B. Okay. Well, one thing I know, this is FCB, which is equal to FBC, which is 720 pounds. 720 pounds. This is tensile. Okay. And you have external force. 300 pounds coming in. Okay. Then you got two unknowns. One is FAB. Actually, FBA, sorry, FBA. The other one is FBE. And we know that geometry-wise, this angle, or this angle, either one. This angle is 45. Well, this angle is 45 too. Okay. Oh, wait a minute. FBE, wait a second. This is not 45, isn't it? Not 45. Okay. Because this angle belongs to this triangle, which is not 45 at all. This is not symmetric here. Okay. So you have to be very careful about this. So you have to figure out this angle, probably. How can you do such a thing? To figure out this angle, we probably want to know, first of all, This angle. Does anybody know about this angle? That means, whoa, what's this angle anyway? Well, we know this angle. We know this is 90. We know this.
Isn't that angle just reflected on the bottom? So you can be able to do that.
180 minus 2 times 22.62.
One.
Because the triangle is the same on either side, so we know that bottom angle there is the same as.
This angle is the same as that angle, yes.
No, I'm talking about on the bottom there. We know
This one.
that angle in the other triangle.
This one.
The BDE triangle,
B-
the small angle.
BDE, yes. This
We
is
know
the
that.
same as that, yes.
Yeah. So
Yes.
So 180 minus both angles will be 134.76.
Okay.
No, it should just be 22.62, the same as joint C, because it's the same angle on both.
Yeah, no, the big angle. The
Yeah,
big.
bring
Oh,
up
the big one.
This angle, this whole angle.
Yeah.
Okay. In other words, because I want to know, okay, very selfishly, I want to know this angle. In order to find this angle, I want to know this angle. So anyways, let's just find out this one. This one is, you said what, 180 minus 2 times something.
2 times 22.6.
2 times 22.6. 62, yeah, 62. Which is
134.76.
134.76. Okay? So, as a result, this angle is, again, 180 minus that.
45 times 24. And 45.24.
45.24 degrees. This is it. Okay. So, let's just set the geometry right to begin. Go ahead.
Is the 22.6 the angle, one of the angle, like if you go back up to the triangle?
Mhm.
Is it,
That's this.
that's that, okay.
That's that. So, that's that, and that's same as that. Yeah, that's true.
Okay, I wanted to make sure I was.
Okay. Okay, so we're going to do, once again, summation of the force. In x direction, this is positive x. Let's just set equal to 0. Okay. This is the 300 minus FBA cosine 45 and plus FBE sine of that angle, sine 45.24 is equal to 0. Again, this is one equation with 2 unknown. That's just the set equation 1. And then again, summation of the force in y direction. It's just set equal to 0. 720 pounds minus FBA sine of 45 minus FBE. FB equals sine 45.24 degrees. Again, this is equal to 0. This is equation 2. So equation 1 and 2 contains 2 unknowns. FBA, FBE. Okay, so you're going to simultaneously solve these two sets of equations. Solving 1 and 2 simultaneously, because you have two equations with 2 unknowns. I'm not going to do a math, so please do it yourself. Please do math. I would actually highly recommend you setting up your calculator if you know how to use your calculator to do simultaneous 2 equations with 2 unknowns. I think some of the calculator have that function. Is that right? So I would highly recommend you master that because in exam you may end up using it. Anyways, this is not math class. I'm not going to go through this much detail anymore. Please do your math. So if you solve those two equations with two unknowns, you can get FAB and FBA, sorry. You can get FBA and also FBE. You should get FBA 723 pounds. You should get FBE 297 pounds. Okay, so please do it by yourself and confirm. And obviously, these are both positive, so the direction of the internal loading is as originally assumed. So FBA is tensile. FBE is also tensile. Okay. Any question? So I found everything, right? I didn't even draw original free body diagram trying to find out support reactions to begin with. You didn't need that. Okay. So occasionally that could happen. Okay. So can you do the same technique for this previously solved problem here? Do you think so? You have to think about it. Suppose if you choose the pin A, force P is known value for kilonewton. You have two unknowns. Yeah, I can find out. Two unknowns. Yeah, I can solve it. And then if I move it to here, using this information to find out those two, yeah, I can do that. If you move it here using those two information, I can find those two. Oh, the only thing I can never find is this. In order to find this, you need the information support reactions too bad. So you have to draw support reaction. You have to draw entire diagram to find out support reactions. In this case, yeah, because otherwise you can never find this internal loading. Okay? But this one, you don't have to. Suppose if I draw one more member here, yes, that's all of a sudden, hey, you have to draw free body diagram to begin with, support reactions first, standard problem. But this is kind of skipping those kind of process. So before you even start applying method of joints, it's a good idea, okay, build your own story. How can I solve this problem using method of joints? What is the most efficient way? Because that's going to save some time. Okay, suppose if you begin with the entire structure, support reactions to begin with, you have to draw entire sketch, support reactions. Okay, next, what's next? Okay, well, next is, let's start with pin A, pin B, and pin D. Then all of a sudden, pin D, wait a minute, BD is zero force member, damn it. I mean, it's going to easily take twice as much to solve this problem, right? Okay. So again, start thinking about what you're doing, especially for this method. Okay, method of joints. Okay. Any question? All right. So next page. Ooh, homework. This homework is actually, oh my goodness, this is symmetric, isn't it? Determine the force P. No, determine the force in each member of the truss in terms of the load P. I think, didn't we do this? It almost sounds like, looks like deja vu. Didn't I do this? Wait a minute. Oh, okay, kind of similar to this case because this is all symmetric structure. So remember what we did? We only find out this, that because everything else is mirror image. Okay, so this is probably fairly simple problem because all you need is this and this and that. So you have to probably start thinking about, okay, starting from B. Well, we can't do that because you have three members. If I apply joint B equations, three unknowns shows up. I can't solve it. Too bad. So you have to start from here. That means you have to find out the support reactions. Support reactions actually gives you those two, and then moving into B, using that information, those two can be found, and then, whoa, that one. So you need a 3 joint, starting also from support reactions. So you have to find out 4 different kind of free body diagram. Isn't that right? So you really need to start thinking about how to solve this problem to begin with.
What is the support reaction at C? Like
Support reaction C, yeah, this is roller, isn't it? So this is free to move in X direction. So you only have Y direction component. This one is pinned, so you can support X and Y. But obviously, this is 0 because this is only force in X direction. So this is probably half P. This is also half P. Well, you can tell, but you have to find out. It is actually a great question here. Support reaction here, what's the reaction force? Let's just review. It's a good idea to review it. Okay. This is something we can review. Note 3, isn't it? So here's a summary of support reactions. It's always a good idea to kind of go back and take a look. So that support is similar to that, because it's free to move in X direction. So if you see a support structure, something like this, support mechanism of one end is actually pinned to support. However, this whole thing is on top of roller. If you see this kind of thing, this is free to move, right? So this is same as that. Okay? Great question. I appreciate that. Because this is obviously different from that. This is fixed supported. So you can have 2 support reactions, X and Y. This one only have Y. Okay? All right, good. So that's what this thing is. Okay? So again, this is very similar method joint-based truss analysis. Symmetric truss. Truss is usually symmetric, but I guess even the structure is symmetric. You can apply non-symmetric loading so that internal loading distribution is non-symmetric. It's easy, can be done. So this is both symmetric. Force is applied in the center line, and the structure is both symmetric. So this is all symmetric truss. Okay. Next homework. Here we go. Let's just take a look. Okay. Determine the force in each member of the truss in terms of the load P, and state if the members are in tension or compression. What is the most important first step for this kind of problem? Anybody? Important?
0.
Zero force members. There are a few zero force members in this structure. Which one is it?
BF, BD.
BD? BD. Because FD and DC are collinear. You don't need this. If so, how about this? Same. Anything else?
FD.
FD. FD. You probably need this. You're talking about the collinear force. Third member is unnecessary. What else did you have? What other constraints, well, what other conditions that you can detect the force member? If only a joint is made up by only 2 members and then you are not applying the force or having support there, that means C. Joint C is made up by 2 members. You are not applying the force here. You are not supporting here. That means this is a force member. Oh, what do you mean? Wait a minute, there's something wrong here. You need one of those. So I guess let's just reconsider here. So suppose if you eliminate those two, okay? If you eliminate those 2 first, what are the other options for zero force member? You can eliminate this, isn't it? So those 3 can be eliminated. So the only essential force is member with the force is this thing. Okay. Then you're going to get started. start with the support reactions maybe in this case. I don't know. Joint B, you can get those two. And joint F says those two are the same. Joint D gets you those two. That, I don't know. You may not need it to have a support reaction. I don't know. Anyways, it's your homework. I stopped saying too much. Okay. So I guess the strategy is, first of all, let's just identify the force member, simplify the truss, and then you need to start thinking about, okay, start from which joint. There are only two unknowns per each joint you can handle. So suppose if you have a 3 unknown forces acting on a joint, you can't support it. So you have to apply entire structure to find out support reaction. Do you need that or not? You have to think about those things before you get started, okay? All right, this is homework 363. Let's move on next page. Okay, so now you are going to get into the method of sections. Method of sections, like I said, this is very effective method, and then, of course, my favorite. Rather than going for method of joints, one joint at a time at all joints, this is very classic statics solution. Because you're a static student, that's probably the better or appropriate solution to begin with. However, once you start taking solid mechanics after this class, you're going to be introduced for internal forces. Internal forces are going to be the starting point to find out internal, like a stress or deformation information. That is the mechanics of materials, solid mechanics. So this is just a sneak preview, sort of. So this is like one step above statics way of approach. So you're going to introduce the virtual cut. This is a key term. Okay, virtual cut. Okay. So if you virtually cut, you are not really cutting the material, but you're going to sort of imagine yourself, if you cut the material right here with this an angle, what kind of internal force you're going to introduce at the cut section. That's what it is. So if you completely cut this member right here, obviously perpendicular to the member's axis, okay? So that means you're going to introduce internal loading, which is equal and opposite each other. Equal and opposite is a key term. In other words, if you try to assemble those two virtually cut members, those two forces cancel each other. As if, oh, nothing happened. You just virtually cut, but you really didn't cut it. So if you put it back in, those two forces cancel each other. Okay? So that's what it is. So internal force is going to be introduced. Now you realize, hey, this portion of the member and that portion of the member, both under tensile force. This is one way to find out, internally speaking, this member is under tension or compression. This is all about internal loading. That's what you're trying to find here, actually. This one too, if you virtually cut here, split this member into two members, each of members are under both compressive internal loading, okay? So we are going to apply this approach. Let's say this is the truss. Oh my goodness. If you try to analyze this with a method of joints, this is a nightmare. Probably no one wants to spend like a few hours trying to go from joint A, joint B, joint C, joint D, joint E. I mean, it's simple, but nightmare. I don't want to spend a few hours just going from joint to joint. Okay? Suppose if you're interested in this member, that member, that member only. I don't care about those two members, for example. I don't need to know everything. I want to know certain members' internal loading because I believe that's a critical member. If so, introduce virtual cut. Just about any location is fine. So this is a cut AA. If you cut like this, you're going to introduce two free body diagram. You're going to virtually cut this structure, pick up either this portion or that portion as a free body diagram independently, okay? then you can apply three equations. Equation of the force in x and y direction, and also moment at any location. You can apply moment at location C, you can apply moment at location A or G or whatever. Summation of moment at any location must be also 0. That's one equation. Summation of the force in x is the other equation. Summation of the force in y direction is another equation. So each one of those free body diagram, you can apply maximum 3 equations of equilibrium. Okay? Then you can find out 3 unknowns maximum. In this case, FBC, FGC, FGF. Suppose if you're only interested in this member, this is good enough. You don't have to start from joint A, B, C, D. You don't have to do that, right? Okay, so this is called method of sections. Let's just take a look at it. Next page. So class example 371, okay? Determine the forcing members. CD, which is this. CF, which is this. And FG, which is this. Okay, so you're only interested in 1, 2, 3, those 3 members. This is called Warren truss. This is, I think, the bridge type of structure. Indicate if the members are in tension or compression. Okay. So I think first thing I want to do is, okay, I want to find out support reactions in this case. So obviously this is the pinned support. The 2 support reactions shows up. Support reaction AX, support reaction AY. Here is a support reaction EY. Okay. So I'm actually kind of going lazy, but let me just start with a sketch. Sketch of simplify the truss. So this is a joint, joint, joint. This is Warren truss. Looks like right triangle all the way through. So I'm going to kind of simplify it. Okay, so this is really super simplifying the sketch here. And right triangle with 3 meters each. And you have a support reaction here, AY. Support reaction here, AX. And support reaction here, EY. And external loading applied here. Location G is 6 kilonewton. This is 8 kilonewton. So I guess the very first thing here is, okay, I want to find out where do I want to cut through, because I want to know CD, CF, GF. So I'm going to cut through this line. This is the cut. Okay, so this is a cut line. I'm going to cut here, and you can either choose this one or that one to begin with. This one or that one. Which one do you want to find? This one or that one? It's your choice. This one seems to be simpler. So I'm going to choose this one because it's a smaller structure. So having said that, if you choose to go that way, okay, you don't even need to know AX, AY. I don't care because I'm not going to choose that structure. So all I want to know is EY. So how can you get EY? How can you get EY straight out?
Some of the forces in the y direction.
Some of the forces in y direction is going to end up having 2 unknowns, EY and AY. That's not a good choice.
So
I would probably, okay, I would take a sum of the moment at A. If I do such a thing, you're going to eliminate AX, AY because those 2 will not create a moment at point A.
but I thought we didn't care about those.
That's
So since
I want to know EY.
So even after we cut it, we can still use the other.
That's right. We want to use only this member. So I want to know EY. If I want to know EY, I'm going to, okay, let's do this. Okay, summation of the moment at location A, that's just set equal to 0. If I do such a thing, what happens? AX and AY doesn't create any moment. 6 kilonewton create negative moment. Negative 6 times 3 meter create negative moment. 8 kilonewton again create negative moment. 8 times 6. And then AX and AY doesn't create moment. EY create positive moment, right? Plus EY times 9 meters. This must be equal to 0. This actually gives you EY straight out, isn't that right? That's all I want. EY is 7.333 kilonewton. That's what I wanted to know. And that's it. Okay? And then AX, AY, I don't care. I don't even want to know because I'm not going to use this side of the cutted free body diagram. So I'm going to just introduce this free body diagram. Now I know EY, that's all I wanted to know. So free body diagram of this cut segment. Okay, that's what I'm going to move on next. So I'm going to pick up this segment. Cut member. Free body diagram. So what I want to know is basically this and this and that. So I just carefully cut through those three members. So now I'm going to kind of try to draw a very accurate sketch. Okay. So this is the joint D. This is what? Joint E. This is joint F, and this is the member CD, but I just cut. And this is member CF, but I cut. This is member FG, I cut. So those are all cut members. And then obviously internal loading is going to be developed. This is internal loading, which is unknown. This is internal loading. Let's call this FCD. And this is internal loading. This is F what? Let me just FC. Okay. And this is internal loading. This is FG. Okay. Let me just zoom in again. So 3 unknown loading shows up. And if you extend the direction of those two forces, this is the location, imaginary location, but this is the joint C. Imaginary location, joint C. And then a little bit more information. So this height, I kind of desire to have this height. The reason is I want to apply moment equation. So this height, what is it? This is 3 meters. What is this height? In other words, this is right triangle, okay? So if you take an angle in between any of those is 60 degrees. Okay, so this is 3 meter times sine of 60.
Do you equilateral triangle?
Yeah, equilateral. So this is 3 meter, 3 meter, 3 meter. But what is the height?
You kept saying right triangle.
Right triangle, sorry. A right triangle is this. That's right. This is wrong terminology. Sorry about that. What's the right word?
Equilateral.
Equilateral. Okay. Sorry, I can't speak English. Sorry about that. Well, I'm Japanese. I can't speak English. Anytime if I do something wrong, I just say, "Oh, I'm Japanese. I don't know English." Anyways, 3 times sine 60, right? So 2.598 meters. That's right. Okay. So I wanted to know this height. Having said this is 60 degrees. Okay. What else do I need? Oh, external loading, don't forget, okay? Well, you're applying external loading at joint F. This is 8 kilonewton. Okay. And also, you found the EY, which is support reactions, you already know. This is EY, 7.333 kilonewton. That's right. Not that much. So you have two forces here at joint F and E. You want to know those three unknowns. So this is the free body diagram. You have 3 equations available. Which equation do you want to begin with? 3 equations means summation of the force in X and Y direction, set equal to 0, and then summation of the moment at any location, also set equal to 0. Any idea?
The sum of the forces in the Y direction.
If you do that, you come up with one equation with, oh yeah.
No, we'd only have one
Oh,
unknown.
yeah, that's a good idea, actually. I would go that. But my regular choice is, taking the moment at C. By doing so, you can eliminate CD and FC's contribution, right? Because those two forces does not create any moment at point C. So you can get FG straight out, okay? But I think the merits are also you can do summation of force in Y, you can get FFC straight out, either way, okay?
You don't make the forces on DE and DF? You don't
DE or FE.
DE or FD, yeah.
Those are still assembled.
What are they?
These are still assembled. Once you
You don't-
introduce virtual cut,
Okay.
you are going to introduce internal force exposed.
Okay.
You're going to expose the internal force, those 3. The rest is still assembled. In other words, okay, if you assemble this structure, connect it up with that, those 3 forces all disappear because it's all internal force,
Oh, okay.
right? Okay. So now what you're trying to do is virtually introducing the cut, exposing those internal forces so that you can apply summation force in the moment to find out those unknown internal loadings. That's what you're doing. This is called method of sections. This is a classic technique. If you start taking solid mechanics, this is the first thing you have to handle. Internal loading, here we go. So what I'm going to do is sum of the moment. So this is the positive direction of summation. Taking joint C, let's just set equal to 0. So this is going to give you, okay, so this is 7.333 kilonewton multiplied by distance from here to there. From here to there, what's that? From here to here.
4.5.
4.5 is 3 meter and half of the 3 meter. 4.5 meter. That's right. So let's just multiply by 4.5. This is going to create a positive moment around point C. And 8 kilonewton, this actually creates negative moment. 8 kilonewton times that. What is that?
That's just one.
This is 1.5, right? Okay, so this is 1.5 meters. And of course, those two does not create any moment at point C, but FFG creates negative moment, which is this distance. That's right, 2.598 meters. All three of them set equal to 0. This is going to get you FFG, which is 8.083 kilonewton. Okay. And next is obviously, if you do summation of the force, either X or Y is fine, but let's just use X. Summation of all the forces in X direction set equal to 0, you are going to have FCD minus FFC. This is what? Cosine or sine or what? Cosine. Okay. So FFC sine 60. And minus FFG. Yeah, so FFG is 8.083 is equal to 0. This is two unknowns. I don't like it. I should have gone FY, but too bad. Anyways, yeah, it was, oh man, this is wrong choice, but Melissa's way is much better. But anyways, I'm going to continue. 0.5 FFC is equal to 8.083 kilonewton. This is equation 1. Now, summation of the force in y direction. This is going to be F of FFC sine of 60 minus 8 kilonewton plus 7.333 kilonewton set equal to 0. This actually gives you FFC straight out. FFC is equal to 0.770 kilonewton. I should have done this before the summation force in X. Too bad, but then from equation 1, FCD is that? FCD is equal to 8.083 plus 0.5 times 0.770, in which 8.468 kilonewton. Okay. So now you got all three internal loading, and obviously I got all positive values because I kind of knew the original direction. But if you have no clue about original direction, you can guess the direction. If you get the negative sign, of course, original guess is flip-flop. So FFG, obviously, this is tensile. FFC, this is tensile. FCD, this is compressive. Okay, so just don't forget about saying either tensile or compressive for each force. Okay. Any question here? This is much easier, isn't it, than joint method of joints. Okay. An important thing is you have to virtually cut and introduce internal loading, which is equal and opposite to the external loading, which is at the cut section. So if you assemble it, okay, all the forces cancels out. Okay. So introducing virtual cut means you're going to actually purposely expose the internal loading for each member so that you can solve those things straight out by applying summation moment and forces in a free body diagram. So this is a technique you're always going to do in solid mechanics. You're going to introduce a virtual cut, pick up either this side or that side of cut segments, set up as a free body diagram, and then find out internal loading. Okay. Any question? So next page is, ooh, who wants to do this with a mess of joints? Anyways, nightmare problem if you try to do mess of joints. The truss supports the vertical loading shown. Determine the forcing member KJ, CD, and KD, and state if the members are in tension or compression. If I'm I don't know, if I'm too frustrated, I can possibly pick up this as a final exam. Hey, go ahead, solve it with a mess of joints. How's that? I'm going to try to flunk everybody here, kind of program. I can do that, possibly. Anything is possible, right? But it is a nightmare. You can probably do it, but you're gonna spend a few hours trying to do joint by joint by joint by joint. Gosh, oh my goodness. But what do you do for this problem? Since you're going to do a method of sections, where do you cut?
You cut like
We
a
cut
straight line from KJ down to CD.
KJ is here, right? KJ is here. CD is here. And KDs. Oh yeah, you're gonna go through this kind of cut, yeah. Then you can either choose this segment or that segment, either way. But important thing is that's the single free body diagram. 3 equations, but you solve it for 3 unknowns. Go ahead.
Underneath it says 12 meters, comma 6 at 2 meters. What does that mean?
This is the total 12-meter wide, 6 of 2-meter segments. 1, 2, 3, 4,
Oh,
5,
okay.
6. Yeah. So this is 2, 2, 2, 2, 2, 2. Total is 12 meters. Yeah.
Okay.
Okay. So this is what, bridge or roof? I don't know. Something made up. But again, one thing I know is you probably don't want to do a mess of joints for this kind of problem. Of course. Next page. This is another homework. Determine the forcing members BC, CG, GF of the truss and state if the members are in tension or compression. Of course, you're going to introduce a cut going through those members. In other words, member BC, CG, GF. So you're going to probably cut through like this. And you can either choose this side or that side of the member, set it up as a free body diagram, and solving internal loading for those 3 members. Okay. Again, single free body diagram, 3 equations of equilibrium to solve 3 unknowns. Okay. All right. I think, yeah, okay. Frames, okay. Let's just take a look at the frames and machines. Now, truss is over. Suppose if you want to, okay, apply the force P right here. This is otherwise the truss member, but you're going to have both pin support. Oh my goodness, both pin support. This actually have like a 4 unknowns. Pin support A and C, and then this is some kind of, I don't know, rigid surface. You apply the force P here on member BC, and also you try to, this is bend. This is called bending moment. Moment is applied for member AB in the middle. This is not the truss at all. So this is much more complicated than truss. This is called frames and machines. Frames and machines are 2 common types of structures which are often composed of multi-force members. Frames are generally stationary and are used to support loading, of course. Machines contain moving parts and are designed to transmit and alter their effective forces. In order to determine the forces acting on a frame or a machine, the members needed to be disassembled into parts, and the free body diagrams must be drawn for each part. That's not simple. In other words, if you disassemble this thing, right here, remove the pin out, remove pin A out, then pick up this member AB. This is under 1, 2, 3, 4 unknown force reactions. Obviously, if you apply equation of equilibrium for this member, this is way too much unknowns. You can't solve it. But the other side of member, if you disassemble B and C, you also introduce 4 unknowns. But those two are equal and opposite, okay? So 2 members having total 6 equations, those are equal and opposite. Eliminate 1, 2, 3, 4, 5, 6 total unknowns. You have 6 equations for 2 members. You can actually solve this problem. Okay, does it make sense? So that's what you probably end up doing next, okay? So this involves multiple free body diagram, all disassembled part by part. Some of the forces are equal and opposite. So if you assemble it, it is going to cancel each other. So this is actually, effectively speaking, only 2 unknowns, not the 4. Okay. Here we go. So this is the class example, but I don't think we have time today to do this, but take a look at it, okay? So this is the, obviously, this is no longer truss. This is the frame. Determine the horizontal and vertical components of force at pins A and C. That means 4 unknowns. This is a 2-member frame, member CB. This is a rigid member CB frame, member AB. So you're going to disassemble, come up with 2 free body diagrams. One is a member AB, and the other one is member CB. 2 free body diagrams. Each free body diagram, you introduce 4 unknowns. Obviously, this is a pin support, introduce 4 unknowns for member AB. And the other member CB, you're going to introduce another 4 unknowns. However, at the member B, 2 forces equal and opposite each other, so it eliminates 2 unknowns. Total 6 unknowns. You have 2 members. Each you can apply 3 equations of equilibrium. Total 6 unknowns, 6 equations. That's how you solve this problem. Okay. So we're going to take a look at it in next class. Do you have any question? Let's stop here today. Let's do a quiz. Any questions? Okay. So let's just stop recording. Let's just do a quiz.